Okay, so here we're going to be reviewing how to balance some chemical equations because that's going to be pretty important when we start talking about stoichiometry and all the stuff we can do with stoichiometry. So, if you don't remember how to write a chemical reaction, here it is. Chemical reactions have a couple parts. We have the reactants on the left side of the arrow. We have the arrow, which means makes or forms, right? It does not mean equals, even though we call this a chemical equation. The arrow always means makes or forms. And then we've got products on the right, right? So reactants make products. That is how we write a chemical reaction. It's always going to look like this. If you've got more than one thing on either side, you're going to have a plus. You're going to have an arrow in the middle. And that's how you write a chemical reaction or a chemical equation. So then the next question would be, if we are balancing this chemical equation, what exactly are we balancing? So remember that little rule about conserving mass? Maybe you don't. If you don't, go back and look it up. Conservation of mass. It's one that you should know. What it says is the mass of a system must remain constant. You can't create or destroy, just rearrange the components. So we are balancing basically the amount of stuff in the products and reactants. And when I say stuff, more specifically, we are balancing the number of moles. So a mole, and you know how chemists love their abbreviations, and we're going to abbreviate mole. Yep, we're going to shorten it a whole lot by spelling it MOL. And what a mole is, if you don't remember, it's a unit of measurement that indicates there are 6.02 times 10 to the 23rd of whatever we're talking about. In the case of chemistry, we are usually talking about atoms or molecules per mole. And this is, of course, Avogadro's number. You all remember Avogadro, right? He's this guy. Yep, right there. Oh, there he is again. Here he is flying in from the back. Avogadro, this guy. Very important to chemistry. So balancing numbers. What exactly do the balancing numbers do? Well, these indicate how many moles of a given substance are taking part in the reaction. They are always placed before the chemical, right? The entire compound. They count for everything in that compound. They are always a whole number. You can see what I wrote in parentheses. But we're going to say right now they're always a whole number. And they apply to all elements, ions, etc. in that particular chemical that they precede. So some examples. Here, all right, we look. We have 2H2, which means we have 4 H's. We have a subscript 2 here, so we have 2 O's. And over here we have 2 H2O, which means we have 4 H's and 2 O's. Another one. Iron and oxygen. Rusting iron. This is the reaction of iron rusting. And so here we have some balancing numbers, right? Because we have iron, we have O2, and then over here we have our balanced iron oxide, Fe2O3. So we need to balance this out since we've got 2 over here and 3 here, right? What we can do is we can put some numbers over here. Right, we know that 2 and 3, those are both factors of 6, right? So we need 6 oxygens because 2 and 3, or sorry, not this 2, this 2. right? 2 and 3, factors of 6. So we'll balance that first, right? Get 6 oxygens over here, 3 times 2, so 6 oxygens, 2 times 3, 6 oxygens. And if we're balancing it out like that, right, and we need 2 times 3 oxygens, we also have 2 times 2 irons, which means 4 over here to balance us out. And here's one more, right? This is, of course, a combustion reaction. We'll talk about reactions in another video. But this one's a little tougher to balance, right? Because there's stuff all over the place. We'll go through exactly how to balance a combustion reaction in a moment. So we've got our C3H8 here, right? 3 carbons, 8 hydrogens. We've got some oxygens, so 3 carbons over here. We need 3 carbons over here, right? 8 hydrogens here. We need 8 hydrogens on this side, right? 4 times 2. So now we look, we've got 6 oxygens and 4 oxygens for 10 oxygens on this side. And so we need 10 oxygens on this side, 5 times 2. There we go, balanced. Okay, so now we're going to work through a couple and balance these chemical reactions. So, lithium oxide, magnesium chloride, making lithium chloride, magnesium oxide. So we can start out here. We've got 2 lithiums on this side, only 1 on this side. So we're going to balance that. That balances out our chlorines as well, right? 2 on this side now. We've got 2 on this side. We've got 1 magnesium here, 1 magnesium here, 1 oxygen here, 1 oxygen here. Great. Everything is balanced. Okay, looking at one that's a little tougher. So, what I always tell people is balance the one that looks like it will be the most difficult to balance. So in this case, I'm going to say phosphorus, right? We've got 5 here, 4 here. So we ask 5 and 4, they are both factors of what number? Hopefully everyone just yelled out 20. So to get 20 on this side, get 20 on this side, great. Look at that. Now we can balance something else. Let's balance rhenium. So we've got 15 over here. We only have 1 over here, so we're going to need 15. Great. Now we'll balance niobium. We've got 12 on this side. We need 12 on this side. Now we're going to look at oxygen, and hopefully oxygen balances out. 15 times 2, 30. 6 times 5, 30. Look at that. We did a great job. Apparently there's one more here. So don't forget that polyatomic ions, they have to go in parentheses, and that the parenthesis goes for everything inside. Now, I will tell people sometimes if this is confusing, right, like NO3, OH, all these things going on, just think about this as X and this as Y, because they appear the same on both sides, right? We don't even have to worry about what's in there. We can just treat them like one thing, X and Y. So here, right, we have 3 OHs or 3 X's, 2 Y's, and over here 3 Y's and 2 X's. So let's balance those OHs first. So 3 and 2, those are both factors of 6, and to make 6 over here, we have 2 times 3, and over here, 3 times 2. Now we can balance out our aluminums, right? 2 aluminums on the left side, so we need 2 aluminums on the right side. And we have 3 calciums on the right side, so we need 3 calciums on the left side. We check our NO3. We have 3 times 2 is 6. 2 times 3 is 6. Great job. and another one. I guess I forgot how many I put in here. Okay, so looking at this one, we're going to look for the one that looks like it will be the most difficult to balance. Probably phosphorus. So now we look, 4, 7, and 4 and 7 are both factors of what number? Hopefully you said 28. So we're going to try this out. We'll go 7 and 4. So far, so good. So now let's balance our osmiums. We've got 21 osmiums here. So we put 21 here to balance that out. We've got 12 manganese. So we put 6 here to balance that out. And now we check to make sure our sulfates balance, our SO4. 6 times 7, 42. 21 times 2, 42. Look at that. We're balancing masters. There it goes. Okay. Which brings us to combustion. Now, these are the steps for balancing a combustion reaction. I would recommend writing these down, so pause the video, write these down. I will say them as we go through it on the other slide. So a combustion example, right? First thing we want to do, double our hydrocarbon. Okay, fantastic. Step 1 done. Now, we want to balance our carbons. So we've got 2 times 39 over here, which is going to be 78 carbons. And we've got 2 times 58, so carbons balanced, sorry. Then we want to balance our hydrogens. 2 times 58, right? Doesn't even matter what that is because we already have 2 hydrogens here, so we put 58 in front there. Great. Hydrogen's balanced. Okay. That, however, leaves oxygen. So what we want to do, we want to add up all the oxygens on our products side, right? So here we've got 2 times 78, which would be 156. Then we've got another 58 from our water. So then we add these up, carry the 1, 214. Great. So that's all our oxygens on that side. Now, we have to remember that we have oxygen in our hydrocarbon, right? Hydrocarbon, it's got carbon, hydrogen. So what happens is we subtract the amount of oxygens here from our total, all right? So remember, we don't have 23, we have 2 times 23. So 46, right? So we've got 168. 168. Now, luckily, 168 is divisible by 2, right? Because if it wasn't, we would have to go back and make this a 4, double everything else. Then it should work out. 168 divided by 2. 84. Now, the very last step, we want to look. If we can reduce our balancing numbers, we want to do that. And in this case, we certainly can reduce our balancing numbers. All right? We can cut them all in half. And there we go. Balanced. So go back, watch that again, write down the steps, follow along. That's combustion. Okay, some things to remember before I leave you. You can never alter the subscripts when balancing a chemical reaction. Balancing numbers are always whole number. Balancing numbers apply to all elements, ions, etc. in a chemical, and it is often best to treat polyatomic ions as one thing when they appear on both sides of the arrow rather than trying to balance each element individually. When they appear as different things on either side of the arrow, usually that's a redox reaction, and we will talk about balancing redox at another time.